Just very briefly, I'm going to say good afternoon to the people watching and also to anyone who's going to be watching this as a recording. Just a few admin notes to deal with. If you happen to be dialed into this but only on the audio side, you are welcome to download the slides which are linked to in the event for today on the front of the website. If you've been looking at the document that's the basis of this presentation, in the last day or so, it changed quite significantly, and I just wanted to mention the fact that it was being edited in a different system. We then uploaded the revised document into Google Docs. The comments that had been entered previously, therefore, vanished, but I wouldn't want anyone to think that they weren't read. It was just part of the editing cycle. The title was also a new and improved one, just in case anyone was thinking, wait, is this the one that I was meant to be at? And finally, this session is being recorded, so anything that you type or say is going to be placed on the internet. And with that, I think I'm going to pass over to Mike.
Okay, welcome everyone. Jamie and I are going to team tag on this presentation. And as some of you probably know, she earlier led a webinar on the organics that are found in primitive meteorites, particularly carbonaceous chondrites, and also in cometary samples. So for that reason, we didn't delete the word icy from the title, the new title, but we do really want to address the issue of where are the major issues and what do we know about primitive bodies in the solar system and their role in delivering organics and water to, especially the young Earth, but also to the other planets such as Mars. So with that, we have prepared a number of graphics here to give you a little more visual information on things that are written down in words, but probably we'll jump over a few of these graphics rather than discuss them in detail. You will be able to access those at your will when you download the presentation. And of course, we would invite anyone to interrupt the remarks at any time, because the whole point here is to gain new insights from you and also to discuss the insights that the team has developed. So this particular document, which is on the web now, was developed by the folks whose names you see here, Penny, Fred, Paulie, Francis, Doug, myself, and Jamie. And so the final editing of the presentation was done by Jamie and myself as recently as this morning. So we take the full blame and give the credit to others for what you're about to hear. All right, so let's move on. Now the issue is, what can we say about the astrobiological significance of comets? What was their role? And by the way, of course, primitive meteorites as well. What was the role in delivering water and prebiotic organics to early Earth? As you'll see in this outline that we're going to present this afternoon rather, depends where you are. The issue is not so simply resolved, because within the last 10 years, there's been a tremendous revolution that has occurred in our understanding of the motion of planets early in the solar system and the way in which that not only mixed the populations of dry and icy bodies radially, but also then changed the understanding of what was delivered to terrestrial planets and when that delivery occurred. It's still an evolving picture. So the other part of the problem is that we really don't have very good information yet on the taxonomy of these icy planetesimals, because it's only been the past 20 years that we've really had the powerful infrared and radio instruments that can permit us to quantify the actual organic composition and water in these various bodies. And we'll talk about that for a bit. So let's go on then and begin with the story. I have to remember to use that little arrow there. This chart shows a cartoon of some of the processes that occurred in the planet-forming phase, actually, running from the collapse of the natal cloud core and the formation of the protosolar nebula, and then evolving towards the protoplanetary disk. And in particular, there are many processes that we now know occurred at that time. Some of them, if I can use a pointer for a moment, some of them actually involve transport, both radially in and out. Some involve transport vertically, shown over here as a circle above the midplane, carrying material up to the region where UV optical and X-rays can penetrate, and of course that represents different depths. But there one can actually see a lot of processing going on in these ways. A lot of laboratory astrochemistry and chemical physics is going on to understand these processes. But as you can imagine, taking these kinds of processes and relating those to what we now see in comets and primitive meteorites is a major story in itself, and one that's developing and will continue to develop for the next few decades, I believe. So that's part of the picture as well. Now, jumping from the nebular phase to the point at which the sun formed, about 4.6 billion years ago, one of the developments that occurred just in the last 3 years was the development of a model to describe the migration of giant planets from their putative formative zones inward towards 1.5 AU and outward again to their current resident locations. This actually occurred within the first 100,000 years or so, and the dynamical simulations actually go on until 600K years. But the key point is that Jupiter and Saturn migrated inward as a result of gas drag. This is all before the gas cleared in the nebula. You'll notice it's long before the formation of the terrestrial planets, and it's long before of course, the moon forming event, which was roughly 40 to 80 million years after formation of the Earth. Formation of the sun, excuse me. The key point and take-home point of this slide is that if you look at the center panel, the particular color bars the color points represent material that was formed either within about 2 AU of the sun or outbound of that. So these would be dry planetesimals in the former case, and icy ones or wet ones, if you like, that were formed farther out. This process, when Jupiter actually migrated inwards and then out again, left this material in the region of the scattered around in the region of 1 to 3 AU. And so it mixed the dry planetesimals outwards and the icy ones inward. Of course, the icy ones would have vaporized or begun to sublime. But if one extends that beyond this to what happened out as far as 6 and 8 AU, what it means is that material that was mixed from one region into another. And so this will play a major role in understanding what was delivered to the growing proto-Earth, proto-Mars, and so on, but also in what role later developments had for subsequently delivering material to the young terrestrial planets. And of course, we need to know the nature of these bodies in order to assess what it was they could have delivered. Okay, so the Grand Tack, as this is called, actually succeeds in predicting a low-mass Mars, and most other models do not succeed at that, so this has given it more than just casual acceptance within the community. We don't know that it's fully correct, and so on. These are, of course, developing things, so let's move on a bit. After formation of the planetary system, let's call that to be at around 100 million years after formation of the sun, a separate dynamical model called the Nice model actually predicts the dynamical evolution of the outer planet region. And it begins at 100 million years with the outer planets now, and they're approximately their current locations between 5 and 14 astronomical units, and they were in the order of Jupiter, Saturn, Neptune, and then Uranus. Why Neptune inside? It's because you need to grow Neptune within that 100 million year interval, and it's difficult to do it if it's very far away. But even Uranus was only 14 AU from the proto-sun, from the sun at that time. There also was an icy disk of planetesimals, and of course, as we now know from the previous slide, this disk probably also contains some material that had been injected outward from the dry region of the protoplanetary disk, the 1 to 3 AU region. Then, as Jupiter and Saturn migrated to their 2 to 1 mean-motion resonance by ejection of planetesimals in their feeding zones, they basically caused a destabilization of the disk at around 3.8 billion years ago, in which Neptune and Uranus now switch places, and the outer disk is destabilized, so is the inner asteroid belt. And both of these classes of bodies then are flung through the solar system, with the icy bodies going primarily into forming the Kuiper disk or out to the Oort cloud. And of course, many of the asteroids and many of these bodies from the isodisk would then be flung through the inner solar system and would bombard the terrestrial planets. So again, this model, dynamical model, which has achieved success by resolving the explanations for about 8 or 9 major conundrums about the giant planets themselves and also their companion bodies such as the Trojan asteroids and so on, has achieved great acceptance within the community. And so the challenge it presents for this particular webinar is to keep in mind the Grantach-Lenese model. I didn't mention the birth cluster model for origin of some placement of some bodies in the Oort cloud in the sun's birth cluster. But these 3 dynamical models together have basically changed the picture dramatically as to what we need to know about the primitive planetesimals, and then also their dynamical delivery and the numbers that were delivered at various times to the young Earth, for example. So the issue then is, since we know they're rich in organics and rich in water, could they have delivered those materials to the terrestrial planets in sufficient abundance to have influenced the emergence of life itself? Okay, so let's move on. We have a lot of things to talk about. So this just reminds you of the reservoirs today. I won't go into that in detail. There are basically 2 for sure, namely icy bodies reside in the Oort cloud and the Kuiper disk. And there may be some in the main belt as well, and we can look to the Grantach as a reason why they might be there. But we don't actually have any detections of water vapor or any other gas released from any of these active asteroids. So it's not clear yet whether those asteroids are activated by collisions or whether some actually are activated by water when the asteroid moves towards its perihelion position. Okay, so how do we get at these questions about the material that is contained within cometary bodies and these icy planetesimals, and how that might be delivered to Earth? Well, this is just a take-home message which says you really don't learn much about the composition by looking at an image of the object. You just learn something about its history. For example, this object is heavily eroded by mass loss, whereas something like Build-2 nucleus has enormous vertical structure, hundreds of meters, spires hundreds of meters in height, and so forth, and is thought to be pristine and not heavily eroded since it was placed in its present orbit. So what instead one needs to do is to begin to look at the chemicals of which these objects are made. And one of the first clues that was quantitatively derived, a taxonomy, if you like, was based on not the primary or native volatiles from which comets are composed, because when this work was done, it was not possible to measure those. One could only measure the fragments that derive from those molecules, and so C2 and Cn are bright and easily seen in the optical. And so a team led by Mike Ahern and his collaborators basically quantified the ratio of C2 to Cn in a number of comets and showed that for comets from the Kuiper belt, they seem to be substantially depleted in this ratio, whereas the relatively a smaller number of Oort cloud comets were so depleted. So this was suggested that this could be perhaps a cosmogonic difference, although other people thought maybe it was due to processing because the Jupiter family comets from the Kuiper belt have been in their orbits for a long time, whereas many of the Oort cloud comets have not. So it also dramatized the need for looking at the individual parent or primary volatiles, as we now like to call them. And this chart reminds you of the 24 or so primary volatiles which have now been detected in cometary bodies. When they've been vaporized and entered the coma, they're in the gas phase, and they are then amenable to detection by looking at their rotational vibrational emissions or the rotational emissions at infrared and radio wavelengths, respectively. What's shown here is two things. One is the range of species, water being at the top, but the other is the range of abundance in a given nucleus. And what you see immediately is that whenever water is used as a metric, you see a huge range of abundance of, for example, CO by a factor of 100 in going from one body to another. And in CO2, almost a factor of 20, and so on. Whereas other molecules show a much smaller gradient. For example, HCN varies by about a factor of 5, and so on. We don't understand this yet. We think perhaps it may be, in some cases, cosmogonic, and that's, of course, one of the key issues in understanding how to relate these measurements to delivery from different regions of the protoplanetary disk to young planets and delivering those to the atmospheric content of those particular objects. I'm going to skip over this so you can go back and look at this later. This is from the Akari Space Observatory, and for some reason I seem to go on to full screen display here. Okay, that's good. The key point is that this was a paradigm shift in our understanding of comets, and it occurred. The paper was published in 2012 in APJ, and until then, no one really understood that CO2 was so important relative to water, or that it was so much more abundant than CO. This was a major surprise, and there was some indication from interstellar chemistry that this would be so, but it's generally not clear the degree to which comets are made of interstellar material. So we don't know whether this CO2 is a heritage of the interstellar medium or whether it was something that was easily produced in the protoplanetary disk. For example, reaction between CO and OH radicals produce CO2 in every collision, essentially. And then you can condense that CO2 rapidly on a grain and enter it into a comet nucleus, and this could be the explanation. So this is still an open issue. The key point is the simultaneity of measurement. And what you really want to do, and this is what is done at infrared wavelengths, is to measure a whole suite of molecules simultaneously. Shown on the left here, you see approximately 9 molecules that are measured routinely in every comet, and then others, isotopologues, which are more difficult to measure, and they are also targeted as well in comet to comet. So this gives you the power to assess how the material is distributed within the cometary nucleus by looking at how it's actually distributed and coming off in the coma. If you see the apolar species coming in one direction and the polar species in a different direction from the nucleus, that suggests strongly that there are two distinct ice phases that are not homogeneously mixed within the nucleus, and we do indeed see that in some comets. So that is another part of the puzzle. Now, just to dramatize this, I've created this cartoon which compares 3 Oort cloud comets. And people who don't study comets tend to think everything in the Oort cloud is the same in terms of its composition. Everything in the Hartley in the Kuiper belt is the same, and so on. But if you look at this, at the low end of the diagram, you see this particular depiction of the overall composition of the comet here, where the blue represents the water vapor and the trace gases are everything else in the small wedge that's just above that. But if you break the trace gases down comet by comet, then for Hartley 2, for example, you find the CO2 comprised almost 80% of the trace gas, whereas for Gerard it was about a third, and for Llewellyn about the same. So here you see a dramatic difference in these three comets from the same reservoir, clearly indicating that they're quite different in their composition. So again, if you look at other molecules differentiated by these colors, you can see, for example, a huge difference in this particular species as you go from comet to comet. So this is a clear indication of perhaps they were formed in different regions of the protoplanetary disk, or incorporated material formed in those different regions, and so on. And this is part of the puzzle that we need to get to, answers. Okay, so I've kind of mentioned several of these paradigm shifts that have occurred in very recent time that are informing us about the nature of these bodies and how they can relate to understanding their role in delivering such material to the young planets. Now, we've tried to group these cometary bodies. The infrared teams have put together approximately a database on roughly 25 to 30 comets. And for the ones that are best characterized, we're able to show that, in fact, the ethane, for example, if one just shows the number of comets and versus the abundance of ethane relative to water, you can see there's a real clumping in this area at around 0.6% relative to water. But there are several comets that are highly enriched by factors of 2 or so, and others that are highly depleted. And we see the same thing in methanol, both or normal, as we call it, enriched and depleted. If one moves on to look at these and order this is actually 17 different comets. I think that their CO abundance ratio. One sees other interesting. Someone mute, please. We're getting a lot of pickup on a mic that's. What was that?
Sorry about that, Mike. I'm just going to mute that line for now.
Okay, thanks. The green region represents CO-rich comets, which are, as you see, they're rare in this population. We only have 4 of them, a total of 18 displayed here. So less than 20, about a quarter, or perhaps 20% of the comets are CO-rich. But when you look for correlations of molecule to molecule, really the thing that jumps out at you, if you look at this for a little while, is that HCN is correlated with ethane, but not with CO and not with methane, for example. And so this suggests that looking at different comets and the correlation of these two molecules might in fact reveal some new information. And sure enough, when you do that, you see that again, the 3 bodies, there's a group that has a high ratio for both. This could be regarded as a mixing line, but most comets are down in this region of the mixing line. Only a few are up at the high end. And there are a few rogues, if you like, which have very little ethane, but a lot of HCN. We think this is a different group of comets. We've called them depleted comets, but we think there's another story behind this, and we're trying to unravel the line of evidence that we have right now. Perhaps these are formed, the HCN in some comets is actually not a primary species, but rather is formed in the coma by some mechanisms. Well, let's move on. We don't really want to get into the details of all this, just to give you the broad brush overview. Another key metric we look at is cosmogonic parameters. These are things we think remain unchanged from the time of formation. As you know, any molecule that has symmetrically located hydrogen atoms will have nuclear spins that can be aligned or anti-aligned. And under exchange, those things are that ratio is invariant. So this gives rise to a temperature, which one can call the nuclear spin temperature. And the key point is that if one looks at different primaries, such as ammonia, shown here, the orthopara ratio for ammonia in various comets approaches the equilibrium value at temperatures above about 35 Kelvin. Water approaches a different value, this curve, and also can be equilibrated at roughly 50 Kelvin. But if you take the spin temperatures and compare them one with another in these two species within a given comet, what's remarkable is that they clump in a very narrow region of this space. And so this tells you that these independent molecular species are registering the same nuclear spin temperature, even though their chemistries are significantly different. And we think that's a very important clue to the formation mechanism. Another thing that's very hard to change in these ices is the isotopic ratios. And the key thing there is to look at ideally the isotopes in individual species. So we'll take a quick look at what is known at one or two of these isotopes, in particular nitrogen, carbon, and hydrogen. So for example, here is a survey done by Manfroy and Jaheen and their collaborators. And for 18 comets, they showed that the carbon-12-13 ratio measured in C2 or Cn, and by the way, keep in mind, these are minor constituents. They're fragments that may even be produced in part from dust. We really don't know all the origins of these two radicals. But the bottom line is that the mean value is in good agreement with the terrestrial ratio for carbon-12, carbon-13. Is that true for nitrogen? No, it's not. In fact, the Earth itself is enriched dramatically relative to the cosmic value by a factor of 2, and the comets are enriched in that ratio 14-15N by another factor of 2. So the 14-15N ratio is about 140 in the mean. There's been no explanation for this, nor has there been any explanation for the enrichment of the Earth itself in terms of nitrogen versus the cosmic value. So this represents a puzzle as to why the comets are different from the Earth. Did they have a role in enhancing the Earth above the nebular value? Is that the reason the Earth is high in nitrogen 14 versus 15 ratio or not?
Mike, it looks like Penny may have raised her hand.
Oh, we have a hand raised.
It was up, now it's gone.
No?
Penny, the lines are open if you want to speak over the phone.
Okay, thanks. Yeah, I was just wondering, to what extent would we necessarily see the preservation of what you were just addressing, the relative isotopes in the rock record of highly geologically active bodies like Earth versus what we might see in much less geologically active bodies like the surfaces of icy moons and so on?
Yeah, I think probably Jamie's better qualified to talk to the meteoritic record on that.
Yeah, but as far as geologically active bodies, I don't have much. I don't know much to say about that.
Okay.
It's a good question.
Yeah. So, Penny, I don't know that. Actually, have not myself looked at the literature as to the where that terrestrial ratio comes from. Of course, as we all know, nitrogen gas is the principal carrier in the atmosphere, but I have not looked at what the rock record tells us. Perhaps someone else on the line could clarify that point.
That would be helpful, and it seems like, and Jamie, that maybe this is, an arena in which some group within the astrobiology road mapping ought to be looking at it, but I haven't read every single paper, so I'm not sure if anybody else has looked at that issue, but it seems that it's important to try to see what, if anything, of that influence of these potential grocery deliveries to the early Earth may have been preserved in the rock record, or where we cannot expect to actually see that.
Well, I guess if one wants to go back to the moon-forming event, you could argue, and this has been argued by various people, that a significant fraction of the outgassing of the Earth had occurred by then, and a lot of that primordial atmosphere was removed during that collision.
Right.
And so then if you deliver a new atmosphere, you would think that, or at least augment it dramatically, then you would think that the nitrogen isotopic ratio in the incoming material would be an important thing to know to compare with the N2 gas on the Earth today.
I was also going to say that if the point of today's webinar is to make sure that we're listing important questions in the roadmap, not necessarily to answer those questions today.
Right.
So this is a good thing to make sure is captured in the document, that this is understanding what the preservation of the isotopic signatures is likely to be. Make sure that that's captured as research that needs to be done. And Francis, I saw a hand raised there. Or is it gone now?
Yeah, I was just kind of going to say what you just said. The question's open. I don't think there is quite an answer. For Earth, it's a little complicated because things have been reset through geologic time, and volatile isotopes are pretty easy to change. I know that there are variabilities among at least Mars and Earth, but I'm not sure we know exactly where those differences come from at this moment.
So we should just make sure that when the final version of this document is written, that that's captured as a question that's needing some more research.
Okay, I think that's an important point.
Yep.
All right, so enough said about carbon and nitrogen. I do want to caution people about accepting the values on the face of them. For example, these check marks on the right compare some issues. The bulk IDPs in Build 2 and 1415 is consistent with terrestrial. If you look at the actual, shown on the left here is a kind of an oval. This is from a figure by Dominique Bachelay-Morvan. And so essentially the bulk overlaps the terrestrial value. The mean, of course, is a little different, but there's an issue as to whether, in fact, the overlap is sufficient at the 1 sigma level. The other point to keep in mind is that in comets, ammonia is the principal carrier of volatile nitrogen. And we have no idea what its 15 nitrogen enrichment may be in comets, so we really don't even know how to compare the dominant carrier of volatile nitrogen in comets with the atmospheric value on the Earth. The next point, which people often tend to forget, is that the origins of cometary CN are uncertain, which comes up to the point that was just made, namely CN can in part come from ice, like HCN, dissociation of a precursor, or from the rock. The dust grains are correlated. CN jets in various comets are correlated with dust grains, and so this raises an issue as to whether the CN is in fact really a faithful measure of the overall bulk in a comet, or whether once we begin to measure ammonia, we'll see a different value. And the final point, which I mentioned briefly in passing, was the fact that we think that HCN may be produced from CN in the coma. So to turn that around, an important sub-question is, how is HCN released from a comet, and in what proportions is it really stored in the nucleus as opposed to being produced in the coma from reactions such as cyanogen plus a hydrocarbon, such as methane.
And a question just got typed in on the chat window there as well.
Okay, so we have, is it Ron?
Yeah.
Outgas volatiles from Enceladus have similarity to what you display for comets. Does this suggest a cometary origin for Enceladus volatiles? That, I think, is an interesting question, one that we've kicked around here in my group at Goddard quite a lot. My understanding right now is that Hunter Waite, who is the PI on the instrument that's measured these volatiles from Cassini, now thinks that essentially most or even all of the smaller molecules can be derived by destruction of benzene. And most of what they see is hydrocarbons, and there is some water. And so it's not clear to me now even what is being released from Enceladus, because by the time you measure something in the plumes, it could have only an indirect relation to the material that actually was being released from the base of the plume itself. So, but nevertheless, the idea of a cometary origin for Enceladus has been suggested. I think it's actually even in the literature, but I think we don't have the hard evidence yet to test that hypothesis. So that's something that one would like to do, and of course now that we know there are plumes of water on Europa at the South Pole, which was just published in Science, we'd like to know whether other species are being released as well. Okay, so now comparing these two metrics has been done by Shinaka and Kawakita and company. And what's interesting is that suddenly what you see is that for a variety of comets, and these, by the way, are grouped by orbital class.
Hang on, son of a bitch. I don't care who it is.
We get good correlation between OPR clustering and the isotopic ratio of nitrogen. But there is one comet, and these are two fragments of Schwarzschild-Bachmann 3, which is an ecliptic comet that's split. They're totally different. So it's clearly something going on we don't understand, and until we do understand it, we can't assess this, take this as a metric to assess what might be delivered to the Earth. Now let's just touch on hydrogen and the D to H ratio, because this is a key metric for many studies, not just for cometary ices and so on. This is work done by Olivier Moussis, and in fact on the right panel it's showing the D to H ratio as a function of distance from the young sun, and this already incorporated something like 5 to 14 AU, which was the region for the giant planets at the beginning of the NEAST model, dynamical simulation. We already know from the case of Saturn what the V-SMO value is. It's basically, I'm sorry, what the D to H ratio is. It's been measured to be V-SMO in methane, very accurately on Titan. So it's right about where the arrow is now, right about there. Jupiter is usually taken to be the nebular value, and that's roughly 2 times 10 to the minus 5. I don't know why he has, this would be a water model at the position of Jupiter, but of course Jupiter itself is really dominated by hydrogen, which is from the nebula. So it is taken as the value for the nebula. Now, for comets, the issue is how do they compare with terrestrial water? And if you had asked that question 3 years ago, the answer would have been encompassed by this ellipse to the right here, that for a total of 7 comets, the mean value is twice enriched relative to terrestrial water. And so this led people to assess the possibility of delivery of Earth's oceans by cometary impacts as being quite small. Roughly 10% of Earth's ocean water could come from comets of this type. But when Hartley 2 was active, Herschel measured the D to H ratio in water released from Hartley 2, which is a Kuiper belt object, and bingo, it was exactly coincident with the value of VSMO within error. And so at this point, people who know little about comets said, aha, this could mean that comets are responsible for Earth's oceans after all. But the real issue here is that one comet does not make a mean. We don't really know what the diversity of D to H is within Kuiper belt population. We don't know what the mean value is. We know something more about where those bodies came from and how they were delivered to the Kuiper belt through the dynamical models, but we yet don't know how many of those bodies could have been delivered to the terrestrial planets during that event. So there are those two things that are sub-questions that need significant work in order to help to assess this question of where did Earth get its water and its organic inventory. So I've kind of captured those caveats and cautions here. You can look at those at your leisure. I don't want to take any more time at this point to do it. I want to move on towards the refractory material. And I have just 2 slides on comets, and then Jamie's going to take over, and because she has much more to say about this through her and her colleagues' work on the organics in primitive meteorites and in the stardust samples. But fundamentally, crystal silicates come in 2 forms, crystalline or amorphous, and it's been a mantra for a long time that if one sees crystalline silicates in comets, they must have come from the near-Sun location, and this implies outward transport of dust from the inner protoplanetary disk to the outer comet-forming region. That was, of course, the mantra when the giant planets didn't move around, when comets were always formed far from the young sun, or the evolved sun, and so on. So this also has to be re-examined in the light of all these new models and so on. But nevertheless, it is interesting that the crystalline silicates have been seen in comets that have origin in the Kuiper belt. That's where they formed. Doesn't mean where the dust formed or where the volatiles condensed, but that's where the comet itself formed. So this presents a major puzzle in itself. And then the mineralogy of those dust particles is the other interesting part of that. Some inclusions have been used to identify interstellar particles that were included within the return cometary material. Others are nebular origin, and I think Jamie will say a lot more about that. But just to stick with the silicates for a minute, the Carnegie Group and others have demonstrated that the dust in Comet Build 2 is formed within probably about 7 solar radii of the young sun. So that stuff is definitely not interstellar, except for some of the high nitrogen 15 inclusions, perhaps. So I think, Jamie, why don't you go ahead?
I actually tried to keep my comments very brief and just focused on some of the questions in this roadmap document that address delivery of organics by icy bodies and the chemistry that go on in icy bodies. And in order to do that, I went to looking at meteorites as well. Part of this is because analysis of organic compounds in comets has been primarily limited to volatiles and spectroscopic measurements that can be made, with the exception of the material returned by the Stardust mission from the VILT-2 coma. The Stardust allowed us to get a little bit of more compound-specific organic identification of some of the complex organics. For example, the amino acid glycine was detected. But there's still a lot we don't know about the prebiotic chemistry, some of the larger organics that might be present in these icy bodies. And this roadmap document is talking about the potential delivery of this type of material from icy bodies and from other meteorites to the early Earth. So I thought I'd look just a little bit at some of what we know about meteoritic organics, what clues they give us about the type of prebiotic chemistry that might be going on in these bodies, and what questions still remain that we hope the roadmap will address in the future. So I wanted to point out here that most of the organic studies that have been done on meteorites are on carbonaceous chondrites, which, let's do this, get my pointer, which are subdivided into 8 subgroups here. And the work that's been done looking at organic inventory of these carbonaceous chondrites has shown a lot of variation among these subgroups. And we don't really know where the icy bodies will necessarily fit, what type of chemistry is going on there. There are similarities between all of these subgroups, but also some differences that lead to questions. We do think that the CI, carbonaceous chondrites, may be the most similar to icy bodies. They're the carbonaceous chondrites that have seen the most aqueous alteration, liquid water present on the parent body. So there's a suggestion that they may be related to comets and to other icy bodies. And I'll show you a little bit about how that may lead to some differences in the organic compounds that are produced. But just to start looking at some of the diversity that might exist, this is looking at the Murchison meteorite, which is a CM2 carbonaceous chondrite. It's the carbonaceous chondrite that's been the most heavily studied for organics. And what we find is a very wide diversity of organic compounds. A lot of insoluble organic matter is this macromolecular material, but also quite a number of different compound classes in the soluble organic matter. And I've highlighted just a couple of compound classes that are relevant to the astrobiology roadmap to understanding the origin of the compounds relevant for the origin of life. So things such as amino acids, amines, purines, pyrimidines, and nitrogen heterocycles, things like that. And we see that there's a large amount of these types of molecules. There's a rich prebiotic chemistry going on here. And in fact, recent studies of the soluble material showed that there's likely millions of different structures, of diverse structures of organic compounds in the Murchison meteorite. And so what we learned from this, if we're looking at the potential delivery of organics from primitive icy bodies that impacted the early Earth or other young planets, is that a very large diversity of these compounds necessary for life could have been delivered. And if we focus in a little bit on some of the molecules that we care about a lot for life on Earth, we can look at amino acids and at nucleobases. And amino acids, we know, are the building blocks of proteins and enzymes and serve a lot of important roles in life on Earth. One of the mysteries or interesting factors about them is that amino acids are chiral. That is, amino acid molecules exist in two non-superimposable mirror image forms like your hands. Abiotic chemistry forms equal amounts of the two. We get racemic mixtures, equal amounts of the left and right hand. But life on Earth uses almost exclusively the left-handed form of these molecules. And the way that life went, that chemistry went from producing these equal mixtures to life using specifically the left-handed is a big question in astrobiology research and origin of life research. What is the origin of that biological homochirality? And I'll show you in a minute what we might learn from meteorites about it and how that extrapolates to some of these icy bodies. I also point out nucleobases because a range of nucleobases and similar compounds have been shown, have been detected in carbonaceous chondrites. You just went. And I show here a variety of compounds, some of which, like adenine and guanine, are used in DNA and RNA in life on Earth, but also some alternate structures that are produced by abiotic chemistry and show up in these meteorites, but aren't used much in life. And so that ties to the final point on that slide, which is that this prebiotic chemistry that occurs on icy bodies, on rocky bodies, can produce a very large chemical diversity compared to the specificity used in biology. And that's an ongoing question of interest to the astrobiology roadmap, I think. Does understanding the diversity and the distribution of these chemicals produced in prebiotic environments or on icy bodies help us understand the origin of the biological specificity, why life uses only the left-handed amino acids or certain nucleobases? And this actually came up a little bit in some of the other roadmap webinars that have happened already. Particularly, we had an earlier one about sources of organic monomers, and some of these same questions were raised there. I've got two more slides, I think. This one is just showing that amino acid abundance varies across meteorite classes. I see we have 10 minutes left, so, okay. What I wanted to point out here is that, my pointer will go, on the left side here are meteorites that have been extensively aqueously altered. They were exposed to a lot of liquid water in their parent body. And we go to about here, these meteorites have seen much less water on their parent body. And this is a logarithmic scale of amino acid abundance. We see that the amino acid abundance is quite sensitive to the amount of aqueous alteration on the parent body. And I think that gives us something to look at as we start to hopefully be able to examine organic inventory in comets with future comet sample return missions, whether these icy bodies where there's more aqueous alteration, more potential for liquid-water interaction, would affect the abundance and distribution of compounds that we see. And the last point I wanted to raise as a question that may be of interest for the roadmap and future research is going back to that homochirality question. Abiotic chemistry produces equal amounts of left and right-handed. Most amino acids and most meteorites that have been studied are also racemic. We see equal amounts of the left and right. But left-handed excesses have been identified in some amino acids and some meteorites. And this plot, again, is showing the correlation of those excesses with aqueous alteration on the parent bodies. And again, the meteorites on the left here, these are just looking at the percent of left-handed excess of the amino acid isovaline in a variety of meteorites. The ones on the left have seen more aqueous alteration and also show more of this left-handed excess. And so we wonder whether there are processes on these icy bodies in these areas where prebiotic chemistry was then exposed to aqueous alteration that might have amplified an excess of left-handed amino acids that then might have been delivered to the early Earth or to other planetary surfaces and in some way helped to seed that origin of biological homochirality. So this is a question for future research. I see Doug just asked about measuring chiral excesses in comets. I'm waiting for comet sample return for that to happen, I think. I'm not sure, I don't know of any way to be able to measure that remotely, the chiral excesses.
It's correct that there's no chiral measurement capability in Rosetta, is that correct?
Yeah, I'm pretty sure that's correct.
I think that is, yeah.
Yeah, so we really need either in situ measurements in comets with some sort of chromatography that can do chiral measurements, or bringing samples back and being able to do those measurements here. And I see Penny asking about destruction of organics during entry and impact onto the receiving target. Would icy materials be more or less likely? That's a good question. That's not one I've thought about much.
Okay.
Mike has something to say about it.
Yeah, I would like to comment on that. The real issue is the entry process itself it benefits from breakup of the body. If you bring in a body that's a kilometer diameter, it pretty much is going to hit the ground before it breaks up. But when you get to maybe 100 meters or less, then the pressure wave which the body encounters as the shock builds up on entry will in fact cause disruption, but it depends on the binding energy of the material itself. So for example, a rock, like a meteorite that reaches the ground, may have a binding energy that's something on the order of maybe 10,000 dynes per square centimeter, whereas a comet nucleus has a binding energy that is much, much smaller, 100 times at least. And so the comet nucleus is going to actually be broken up fairly easily, and the fragments will be decelerated quite easily. And they will essentially reach the ground pretty much intact and deliver their organics as they do that. The stonies, like the carbonaceous chondrites and so on, and Murchison, so on, those bodies reach the ground as fragments that range in size from millimeters to meters, and they also deliver their materials to the ground intact. But it's the small particles that are entering, say, on sizes on the order of millimeters and so on, like IDPs, that basically are going to lose almost all their organics because they get superheated and even get vaporized and so on.
We're running out of time here.
Yeah.
I just want to say I noted that down as perhaps something, again, to include as in the roadmap document that, again, I think I'm noting some of this down, the document. I will make sure that gets into the final document of this to go into the roadmap.
Yeah, these are very valuable comments.
Yeah, since the point of this is to come up with where we want to go with research for the next 10 years, it's very good to have these comments.
Now, Andy and Mike, I suppose someone's going to send us this list of comments, is that right?
It is. You can get the comments, but given that we are just coming to the top of the hour, I was going to take a moment to mention to people that the document that this presentation is based on is now open for comments, just in case any of the people present or anyone listening to this hasn't done that before. All you have to do is click on the link, and that will take you straight to the Google document. We do request that if you have a Google ID, you log in with that, purely because it helps the authors then see who's making which comments. If you don't have a Google ID, if you could just note your name down on the comments in case they need to get back to you. And just to be clear, the overall process, exactly as we've been doing here, is to note any questions or ideas that could help strengthen the paper, because we are coming to the end of the process. We still have a few weeks for people to be able to put their comments in, but now would be a great time to do it. So we'd encourage you to go back to the paper, insert any comments on that, and yes, everything that's been entered into the chat box will also be available now. Are there any last questions, or do the presenters need to make any last comments before we wrap it up?
I think this was the last slide that Mike had, was just some references there.
Yeah, we're going to post a bibliography and so on in our next go-around, so I think that'll help people somewhat in getting back into the literature and looking at things in more depth.
Excellent. Well, in that case, thank you very much for a great presentation, and we hope to see everybody's comments being popped into the Google document. All right?
Good.
Thank you very much.
Thanks to everyone who contributed. It's been great.